Okay, I think we can try to start. It's my great pleasure to have Feliciano Giustino as a speaker for today's MSc/chemistry seminar. Feliciano is a friend, and we met, I would say, several years ago when he was a lecturer at University of Oxford, England. Before that, he did his PhD in EPFL in Lausanne, Switzerland, and then came to the US in Berkeley for a postdoc, and then Oxford for a bit more than 10 years. And now he's a full professor and as an endowed chair in both the Department of Physics and the Oden Institute for Computational Engineering and Sciences at the University of Texas, Austin. And Feliciano is one of, his research is on developing tools for electronic structure calculations, mostly for materials. So he's going to present us his research applied to transistors, but his research interests really span many different fields, including chemistry. And so I hope we'll learn some of the cool stuff that he and his lab are doing these days. Thank you, Feliciano.
Okay. Thank you, Oliviero. Thank you so much. Thank you, everybody. Can you hear me at the back? Okay, cool. So maybe I'll stand here and point to this one if that's okay with everybody. Is that okay? Sorry for giving shoulders to this side. So first of all, thank you, Oliviero, and thank you, Elton, for bringing me here. I think it's my first time in Boise, and it looks fantastic. So you're really lucky. I'm working at UD Austin, and I work in two places: Department of Physics and the Oden Institute. I will say a few words about that in a second. And today I would like to just share with you some of the work we've been doing in one of the areas of focus of our group, which is computational modeling on materials for next generation electronics. Okay, so we are a theoretical/computational group, but I don't expect anybody to have a background in that. I will try to keep it as general as possible, and also feel free to stop me anytime if you have any questions. So just a couple of words about Austin. So if you've never been there, so we are sitting more or less in the center of Texas. UT is a public institution like Boise State, and it's the flagship campus of the University of Texas system. It's a very big place. We have 55,000 students. And there are just a couple of things that I would like to maybe highlight. One thing is this Oden Institute that Oliviero mentioned. So what this is actually is a research unit where we are about 30 faculty. All of us have a split appointment. So 50% of the time we spend in this building and 50% in a department. In my case, it's physics, but other colleagues have departments in medicine, chemical engineering, mechanical engineering. So the common theme is that everybody there has some kind of interest in applied mathematics and scientific computing and high performance computing and programming. Okay, and that's what brings us together. So to do that kind of work, we actually use a facility that is called TAC, stands for Texas Advanced Computing Center. So this actually was 25 years ago. It was a small computing center at the university, like every university has. But then the people working there managed to really be successful with the National Science Foundation, attracting more and more grants to buy bigger machines. And today this has become the flagship institution in terms of supercomputing for the National Science Foundation. In fact, just to give you an idea, we currently have Frontera, which is the largest academic supercomputer in the world. And next year, this center will deploy Horizon, which is the next NSF machine. And this machine will be hosted in one of the large data centers by Dell, north of Austin. And is about a $500 million computer, essentially. So this is going to essentially place the US at the forefront of computing for the next few years, hopefully. So there are three things we do in my group, and then they can be summarized in the following way. So the thing I'm really interested in is quantum theory of solids. So think about solid state physics using quantum mechanics. That's really what we are interested in. To do this, we use large computers. So there's a picture of the Frontera supercomputer. and we develop software to run on these computers. So I would say that probably in my group, 80% of the time is spent writing on debugging code for everybody, from students, undergrads to postdocs, okay? And then ultimately, all of this is done to try and contribute to material science. So the goal is to try to be of use to some of our experimental colleagues. And maybe the dream is to try and do a little bit more, that is to really discover new materials. So I'm sure that you heard about using computational tools to discover materials on the news, AI, machine learning, all these things. I just want to mention that this is not just wishful thinking. If you spend a lot of time on these things, at some point, you might get lucky and really predict materials that will exist at some point. And these are just examples of a few compounds that in my group we have designed. Okay, that means using ab initio calculations, and then they've been synthesized by our collaborators. So these things were not existing before our calculations, and these are basically these powders that look a little bit crappy here. They are something that now has been made into large single crystals. They are used in many devices, and they are mostly on this side halide double perovskites, and this was in an oxide perovskite. Actually, for all of those, we managed to file patent applications. We got some patents awarded. Some of them are licensed, and the postdocs who work on this, they're getting royalties every year for the use of these materials. And one funny story about this is that maybe the one that doesn't look as great is this kind of powder here. So this is the only one for which we did not submit a patent application. The reason is that when our collaborators measured the optical properties, they told us that these spectra look really bad. That means that this compound is extremely defective and it must be worthless. And just 1 year after, the group of Ted Sargent demonstrated that you can use this as a white light emitter, and this carries near unity quantum efficiency. So this essentially is the first material that emits directly white light without combining red, green, and blue LEDs. Okay, so this is the only one for which we did not submit a patent application, and this is of course the one that is not being used in some LEDs that are being commercialized. So I guess for those of you who are working on materials discovery, the take-home message from this slide is: if something looks really bad, try to patent it anyway, because you never know. So this is a more recent compound that we've been working on. It's actually, we did a lot of work on perovskites, which are compounds that have this kind of structure with octahedra, and then they're corner sharing and things like that. And this was mostly on halide or oxide perovskites. And at some point we asked, can we do something more kind of crazy and go for completely different stoichiometries and elemental composition? So we looked into nitrides. And the interesting thing on nitrides is that the perovskite has a structure which is a formula unit which is ABX3. So when you have nitrogen, which is 3-, the N3 brings us to 9-. So the A and B site should be adding up to 9, +9, okay? So that means that the two cations are extremely oxidized, and that's very difficult to achieve. So we did some thermodynamic studies with basically DFT calculations, and we predicted that this object should exist, should be stable, and should be a ferroelectric semiconductor. And when we did that, we tried to publish it. The reviewers destroyed us, of course, because they told us there is no chance that you can make cerium 4+. Then when we got past the reviewers, the editor told us, even if the reviewers agrees now, I don't agree, so you should not publish it in my journal. Then we tried to push it, and at some point they let us publish it. And then a year later, 2 years later, the group of, basically a group in Peking University managed to synthesize it. So they did molecular beam epitaxy of this perovskite on top of strontium tatanate on a silicon wafer. And they managed to realize exactly the phase that we predicted. And they managed to demonstrate that this is actually a ferroelectric. So this is just one example of cases where sometimes even if people don't believe us, a few years later, we get lucky and people realize the materials that we have invented. So the take-home message from this slide is don't give up. If nobody believes in what you're doing, maybe some years later, somebody will recognize that it was worthwhile. Okay, so this is basically just to say that we are working in the area of material science. Now we'd like to dive into the main topic of this presentation, and this is about electronics and trying to study materials for electronics. And this is going to be mostly 2D materials, and I know that some of you are experts here in this field. So I just want to motivate why people are interested in these things. So this is just a conceptual picture from the Semiconductor Research Corporation Sustainability Report from last year. So the point on this slide is to show that the energy required for computing and for communication is increasing at a very fast pace. So we always get told that electronic devices are getting more efficient and more energy efficient and faster. But actually, the demand for these capabilities is outpacing the rate at which you make devices more efficient. So as a result, the energy used for computing is actually increasing exponentially. So what is happening is that what people expect is in 15 years, the global energy consumption will be impacted pretty significantly by computing. And just to place that in context, I'm sure that we were discussing at lunch with some of you about large language models. That's one prime example of demand for raw compute power. So this is just a slide from actually already 2 years ago. That's pretty much outdated now, to show you how much energy it takes to train some of these language models. So this is pretty old. This is GPT-3. So GPT-3 essentially required about the equivalent of 500 tons of carbon dioxide emissions. And one of us would spend in 1 year 5 tons of carbon dioxide, okay, in terms of power. And this was GPT-3. So if you look at GPT-4, which is already older, maybe 2 years ago. So to train that, it took 5,000 tons of CO2, which that means it's 1,000 US households for 1 year. Okay, so this amount of energy is enormous. And actually, this is GPT-4. So imagine what happens with the current GPT-5 and what will keep happening as many more companies develop new language models. Okay, so the amount of power that is being required is enormous. So a lot of companies are looking into how to address this by developing new concepts, new ideas, new devices, new materials. And there are many, many directions. So it's probably too many to discuss. But there are many very interesting ideas like photonic circuits, neuromorphic computing, quantum technologies like quantum computing. The one we've been focusing on is much more humbly to try and see whether one could have some materials that could replace or complement silicon in next generation kind of devices. And this is going to be primarily two-dimensional materials. And this is done within the context of a consortium of the Semiconductor Research Corporation, where we are one of the theory groups, and where also Elton here is one of the experimental partners, essentially. So the idea of this consortium is to develop new materials for next-gen electronics. So this is a crash course on what a transistor is, and I'm sure half of this audience at least will know much more than I do about this, but let me refresh for the other half who may not be as familiar. So the idea here is that in this device, one would like to draw a current from this side to this other side. So this is what people call the source, and this is the drain. And you draw a current through this semiconductor, which is typically silicon, by applying a voltage between these two terminals, okay? So just like a battery. Now, that would not be a transistor. So to achieve a transistor kind of effect, what one does is also to apply a voltage from another terminal here, which is called the gate, and is separated by an oxide from this source and drain parts. And the action of this voltage is to kind of function as a valve. So by changing the voltage, you control the flow current. And by doing that, you can achieve realize logic operations like, from 0 to you get 1, or you get the additional 2 bits or things like that, okay? So this is the most essential component of every chip that we use today. And this is a typical current voltage characteristic where you see how the current depends on the drain to source voltage, and how this plateau here is modulated by the voltage between this gate here and the source, okay? So we say that the transistor is on when you are in this plateau. And this is basically, this plot is kind of the basic of all logic operations we use today. Now, this is how transistors were looking half a century ago. So this is the kind of layout that you would have found in 1971. And that was a time where there were only 2,000 transistors on a chip. And the distance between this side and this side would be something on the order of 10 microns, okay? So things have evolved since then, and people have tried to pack more transistors, meaning more capabilities on the same chip. To do that, you just have more of the same, but you make them smaller. So the idea is to reduce the size of this little bridge here, which is basically the channel. And now the typical channels 10 years ago was of the order of, let's say, 20 nanometers. Okay, silicon has a unit cell of half a nanometer with 2 atoms in that space. So that means that there are maybe 80 atoms across from here to here, right? And in this case, in order to have better electrostatic control of the electrons flow in the channel, they raised this gray thing here. So in order to have the gate on 3 sides, okay? So this is called the FinFET, simply because the channel looks like a fin, the fin of a fish. And this was 10 years ago. And then a few years ago, people went further down this road, and they tried to realize basically a situation where the gate is on 4 sides, so even better control. And that means thinner channels and shorter channels. In this case, this is probably what you guys are using now if you have an iPhone. And this is a 4 nanometer process, means that roughly you have maybe 16 atoms from this side to this side, okay? So this is just to say that the current electronics is going to a point where what happens at the scale of individual atoms matters, okay? So for us, that's great news, because it means the quantum mechanics that we learn and we study might become helpful in studying this kind of materials. So just to now talk a little bit about figures of merit. So what people would like to do is to make these things faster and to make them consume less energy. So there are many, many design criteria, and designing these things is a whole art, and there are people specializing for decades on this. So I just want to oversimplify it and just say that this plateau here, the saturation current, apart from many, many details, is directly proportional to a single materials parameter that is called the carrier mobility. I will say more about that, but the mobility essentially is the ability of electrons to move fast once you apply a voltage, okay? So this is important for the saturation current, and is also important for the time to rise, which is basically the time it takes for the current to go to full level that you would like to achieve. So this is what determines the clock frequency of your chip, so how fast it can make logic operations, okay? And this is inversely proportional to the mobility. So in practice, to make these things better, it is desirable to take this number and make it as large as possible, okay? So what has been happening with this kind of developments in the layout of the transistor is that the size and the thickness of the silicon channel where the electrons go through has been changing. And in particular, the size or the thickness of the silicon layer has been shrinking from microns to the level of nanometers, right? Now, there are very interesting measurements where people demonstrated that if you take the mobility of silicon, that's a bulk crystal, which is typically 1400s in units of centimeter square per volt per second, as you decrease the thickness, this number starts going down. And if you go here even more below 2 nanometers, the number keeps going down. So at this level, essentially, the mobility is about 5 instead of 1400. So the impact is that you're going to consume much more energy. Your chip is going to heat up much faster, and this is problematic because it's very inefficient. So what people would like to do in this field is to try and check whether one could replace silicon with something that maintains a very high mobility, even in the limit of very thin channels, let's say in the nanometer regime, okay? So before getting there, one could ask, why is it happening that the mobility drops so dramatically? So one concept that people have been thinking about is that what is happening is that as the silicon channel in this cartoon gets smaller, the fraction of electrons that travels very close to the interface with the oxide is increasing. So it's a surface to volume ratio problem where too many electrons are traveling close to this region, which is essentially amorphous and causes a lot of scattering, okay? So this is something that is unavoidable once you keep thinning the silicon layer, because it will always have an amorphous oxide on top. So what people have thought in this area is that maybe one way to go around this problem is to replace this object with materials that have perfect interfaces by design, okay? And I'm sure that you can tell where I'm going. So this is a cartoon from now more than 10 years ago, where people were proposing that if you look for two-dimensional materials that are bonded by a van der Waals bond, so very weakly bonded between layers, you might be able to realize interfaces where this your semiconductor channel is kind of decoupled from everything else. And because of that, electrons that travel through these channels may not scatter as badly as it happens in silicon, right? So this is pretty much the main premise of the research on electronics based on two-dimensional materials. So this is pretty much the dream, and there is thousands of groups in the world working in this area. And this is a little bit more close to reality. So this is an EDX, energy dispersive X-ray analysis of a cross-section of a molybdenum disulfide transistor. So this is source, drain, gates on two sides, and then this yellow thing is the moly disulfide. Okay, so if you go looking at the mobility of these objects, you find something that is not as impressive as one would have wanted. This is the same plot I showed you earlier for silicon that is basically the mobility is dropping as a function of thickness. If you take two-dimensional materials, the mobility actually hovers around the value of 100 centimeters per equivalent second. So it is better than 10, of course, but it's not as good as 1400, right? So it seems like despite the enormous amount of work on two-dimensional materials that has been happening in the past 15 years, people could not find two-dimensional materials that can deliver extremely high mobilities that would be worthwhile, that would be enough to justify replacing silicon in production lines, essentially, okay? So the question we had from our kind of partners in this consortium where we're working in, that can you do something about it? Can you give us some guidelines on how to design materials that could have higher mobilities? And can you maybe try to model entire transistors? And then we can try to bring that together with experiments and come up with new solutions. So what we've been doing in our group is to try and work on something that looks like the following. So this is a simplified schematic of what we would like to model. What you're looking at here is the semiconductor channel. So the purple would be molybdenum, yellow would be sulfur, and then this would be where the electrons go through. This is a contact, like a metal contact. In this case, it would be gold. And then you have two dielectrics in this case, for example, hafnia. And then these are separated, they separate the channel from the top and bottom gate. So this is the simplest possible model of a two-dimensional transistor you can imagine. And the question is, can we do calculations directly on that? Now, I could tell you, yes, we can do that, no problem. The truth is actually we cannot at this stage. So this system is way too complex for realistic calculations. So if you go around, there will be, you will find many pieces of software that allow you to model that, but the reliability of the results is not really guaranteed. So what we know today is that this, at this stage, in this shape, is not doable yet. So what we started doing in the group is to break this down in pieces that we can handle with the controlled accuracy. So the first piece, for example, if you try to model something so complex, is to look at the basic. The most important part will be the channel. So maybe we should study what happens if you have only the channel in this device. And that would allow us to tell what is the best possible theoretical performance if nothing else happens to the system coming from interface and contacts and so on. So that's something that I'll discuss in a second. The second element is to see what happens if you have an oxide, so below or above the system, to understand whether that will affect the transport of electrons in this layer. And the third question would be, what happens if you have metal contacts? So in the end, you need to inject electrons from one side, you need to take them out from the other side, and there would be an interface here which acts as a barrier for the electrons. I want us to understand what happens to the electron quantum wave functions when they need to jump from this side to this side, okay? So in the following, I'll tell you mostly about the mobility, so the pure material, and then I will say a little bit about the oxide and these contacts. So I mentioned the word mobility earlier. So now let me give you a bit more of a formal definition. So this is just a cartoon of a crystal, and you can imagine that if in this crystal there is no electric field, electrons at some kind of room temperature will wander around in some random Brownian motion. So they will be scattered by maybe vibrations, defects, and other things. But on average, the velocity will be zero because there is nothing that breaks the symmetry, essentially. If you now apply an electric field, you are breaking the symmetry in this direction. So the electric field will accelerate this electron in between successive scattering events. And as a result, the trajectory will be stretched in the direction of the field. So if I start from this side, after a little time, I will find myself here. So the electrons, we say, acquire a finite drift velocity. So we call mobility the coefficient of proportionality between the velocity and the applied electric field, as simple as that, okay? So that's what we would like to calculate. And now this is a cartoon. The question is, how do you use quantum mechanics to perform a calculation of this object without employing empirical parameters from experiments? So the way we do it is to use something called the Boltzmann transport equation. So if you studied transport in gases, transport of neutrons, or in plasmas, this is exactly the same equation. So in the Boltzmann transport equation, what one does is the following. Instead of trying to study the behavior of every particle, one takes a collective kind of description and asks how many electrons I will find, for example, in this little box at a certain time, and how this number changes with time. So this is described by this equation, which is the Boltzmann transport equation. The left-hand side is what is called collisionless flow. So that means that this is basically accounting for the fact that maybe if I have 2 electrons to start with, there may be another one coming from the left because this has a finite velocity that is positive, so it's moving towards a positive x. Then there will be some electrons that maybe are coming from the bottom. This is because they have some kind of change of momentum coming from an external force. And then there will be some electrons that will come in or out of this box because they are scattered. For example, an electron here may bump into an impurity and find itself into this little box. So the Boltzmann transport equation is a way to keep tabs on these effects and try to count how many electrons you find in a certain region of your phase space at any given time. In practice, what we do is to remove the dependence on space. We consider homogeneous materials. We remove the dependence on time because we want steady state carrier kind of currents. And then we replace this rate of change of the momentum, simply use the Newton's equation. This would be the force acting on the electrons. And this is replaced by the electric field plus the Lorentz force. So if you are doing Hall measurements, you will have to use a magnetic field. So that's what goes into this expression. So this is what we try to solve in practice. Now, this description is for classical systems. What happens when you have a material that is quantum? So I'm sure that you know that crystals have electrons sitting in well-defined energy levels that are characterized by one energy, one wave vector, and one index that tells you the band where the electron is sitting. Okay? So the problem of solving the Boltzmann equation for this kind of system is essentially asking, what is the occupation of these electronic states after you apply an electric field? So in a transistor, for example, if you have an N-type moly disulfide, most of the electrons will be localized around this kind of little region of the phase space. That's the bottom of the conduction band. Now, if you don't have an electric field, you will have as many electrons on this side as you have on this side. So since the slope is the velocity of the electrons, the net velocity in this example will be 0. So there is no current going through the sample. If you apply an electric field, suppose going towards the left, the electric field increases the momentum. Since in quantum mechanics, the momentum is the Planck constant multiplied by the wave vector, the electrons with this wave vector will be pushed towards the right. So the net result is that there will be a little bit of extra electrons here, and there will be less of electrons, fewer electrons on this side. So this imbalance means that there are more electrons with positive velocity than electrons with negative velocity. And because of that, you have a current. So the goal of calculations of transport is to determine how this distribution looks like when you apply an electric field, right? So that's pretty much what we calculate. And it is done using techniques that are first principles. They are based on a combination of density functional theory and many-body perturbation theory. I will not give the details, but I'm happy to discuss the technicalities if you are interested later. So this is just 2 benchmarks to show you how predictive these calculations are. So this is a calculation of the carrier mobility of silicon for electrons in silicon as a function of temperature. The yellow symbols are experiments, so measurements of drift or Hall mobilities, and the red line is the calculation. Okay? So please note the red line is not a fit to the data. It is a calculation done without any parameters from experiment. In fact, the only parameter in the calculation is the number 14, which is the atomic number of silicon, and that's it. Okay? So this is basically to say that we are getting to a point where calculations are very, very predictive, okay? Even though they're very expensive. Now we wanted to discuss 2D materials, so let's see how does this do for 2D. This is an example for a molybdenum sulfide, and this is the calculated mobilities for holes and for electrons. So in the range of 100, room temperature. So if you take experimental data, they are scattered, over a wide range because many different groups report different samples with different quality. So here I'm showing just an error, so a bar that tells you we found data from this point to this point and from this point to this point. And I would say that this is telling us that the calculations are fairly predictive given the experimental uncertainty on the system, so we are in the same ballpark. So with these benchmarks, the question becomes, okay, now we know that we can kind of calculate mobilities with reliable, in a reliable way. So what can we do with that? So the question from our kind of sponsors and collaborators, experimental collaborators, was, can you identify materials that have a much higher mobility than these values here? And the way to do that is to search through possible materials and calculate the mobility for each of them and see which one wins, all right? So what we did here is to start from databases that other groups have developed. So this is one of the popular ones. It's called the Materials Cloud 2D database. So this was built in a very interesting way. So you go to the ICSD, which is the Inorganic Crystallography, Inorganic Crystal Structure Database, okay? So it's a database of all known crystals that have been synthesized with XRD data and so on. You identify all crystals that are layered. And for all of those, you calculate the exfoliation energy, okay? So exfoliation energy just means you take the energy of the crystal minus the energy of the, alpha crystal separated, away. And if this energy is comparable to that of molybdenum sulfide or graphene, these have been classified as easily exfoliable, okay? Out of these 186,000 compounds that are known, they identified 5,000 layer structures, and out of those, about 2,000 are easily exfoliable. So the idea is to look at those and see whether we find something that is interesting. Note this database contains materials that are not all these are being realized in 2D form, okay? So some of them are hypothetical. So what we did here is to take these ones, out of 5,000 actually, you need to look at dynamical stability. It means if you put it together, will it collapse in front of you? And actually looks like only 260 are dynamically stable, meaning that they don't need a substrate to exist. And out of those, we started doing simple calculations. For example, you can calculate the band gap. That tells you whether you have a metal or a semiconductor. We would like a semiconductor. So that basically reduces the number to under 70. Then you calculate the carrier effective masses. If the effective mass of the electron is very heavy, it's not going to be a good semiconductor. And then you keep going like that until you find a bunch of materials that you think are the most promising, for which you can do very advanced calculations. So in our case, this was basically 16 compounds. For those, we did the best of the best that we could. And this part actually usually is the most time consuming. For example, if this screening costs maybe 1 month of computing time, this one here is maybe 6 months only for 16 compounds because it's much more advanced calculations, okay? So this is a summary of what we found. And there are 2 points I want to make out of this slide. So these are the compounds we looked at. So one of the points is that these are calculations of intrinsic mobility. That means there is no impurity whatsoever. These are perfect crystals in the model. There is only vibration, so phonons, that affect the electron transport. So if you look at this side of the plot, the numbers are 6, 14, 35, 13, 45, 15. So they're all extremely low. So what that means is that most of these 2D materials, without any imperfection, are not great conductors, okay? And the other interesting bit that one can observe is that there are a few that are pretty outstanding. So you see 900, 1200, 1300. And then if you go down and look at them, tungsten diselenide, tungsten sulfide, antimony. So if you've been working on 2D materials, you will know that tungsten disulfide and diselenide are pretty standard 2-dimensional semiconductors, okay? So it's a little bit of a surprise that going through a database that starts from 180,000 compounds, you do all this work and then you end up with things that are already known. And in particular, what we found is that these materials have extremely high mobilities for holes that are not observed in general. So if you look at the experiments, these things are nowhere to be seen, right? So the first observation was actually, first reaction from colleagues was, your calculations must be wrong because clearly you're completely off base here. And at this point, what you do is to try again the calculation. You try to understand whether we're doing something reasonable or it's something wrong with your setup. So this is just an example, which is one of the two, the tungsten diselenide. So the first question was, are the calculations correct? And the answer is, well, as far as we can tell, after repeating them many times, they seem to be correct. But the prediction is up here, but while the experiments are all in this ballpark, mostly around 100 and some, all the way up to 200, but nobody can go up to 900. So what's going on? So the second question that we ask is there any physical reason why the mobility could be so high? Is it just a fluke of the calculation, or there is a physical basis for it? So if you look at the band structure of this compound, it's actually quite interesting. So this is the band structure from in the Brillouin zone, which is represented here. So this line gamma to K to M is gamma to K to M, which is not here. Now, what is happening in this system is that tungsten has a pretty strong spin-orbit coupling, okay? Because of that, the valleys, so the two bands at the K point, so near the top of the valence band, actually are separated by almost half an electron volt. The second consequence of spin-orbit coupling is that this valley and this valley, they acquire opposite spin polarization. So if you represent the spin as a color, what you discover basically is that this valley here would be this thing here. So it will be spin up, spin down. Since it's spin up and spin down, the electron cannot scatter from the top to the bottom valley. Now, what you also discover is that if you go to the next valley, the spin polarization is reversed. So this is a typical standard valley polarization well known for TMDs. Since it's reversed, this guy cannot scatter into this guy because they have opposite spin. But also this guy cannot scatter into this guy because the energy difference is too large and there must be energy conservation. So if you change energy, that energy must come from a phonon, but there is no phonon with an energy as large as half an electron volt. So also this mechanism from here and from here are forbidden. And then the scattering from this point to this point is also forbidden because the gamma point here is about half a volt below the top of the valence band, and therefore it cannot satisfy energy conservation. So bottom line is that because of spin-orbit coupling, most scattering channels in this system are completely suppressed. So this is just a symmetry in physics, nothing more. And because of that, I think this gives us confidence that these results are not just an artifact, but actually they come from some physics. So at this point, we started pushing and talking to experimental colleagues and discussing what can happen here. And then we realized that okay, let's do something that we are not done, including impurity scattering. So if you start incorporating impurity scattering with the levels that are observed in experiments, which is about 10 to the 12 impurities per square centimeter, this value drops down here. Okay, so you go from 900 to 50. So what that suggests is that maybe these materials have very strong potential for delivering extremely high mobility, but the imperfections in the crystal is what causes these poor values observed in experiments. And at this point, one could ask, okay, then it's a matter of improving samples. Is this even possible? And this was actually demonstrated last year. This is a group, I think this one on the left is Phil King at Harvard, and this one on the right is Corey Dean at Columbia. So these are very high purity samples of tungsten diselenide, and these are the mobilities measured as a function of temperature. So if you go down here, room temperature, 1,000 and a little bit more than 1,000. So they realized what we've been seeing in the calculations. Then after we've seen this, we repeated all the calculations as a function of temperature. So the green lines are the data from Harvard, and the gray lines are our calculations. So as you can see, again, almost perfect agreement. So this is just to say that, even though the calculations seem very odd and very different from what one would expect, sometimes they have predictive power. So they can be used to motivate new experiments to look into these materials a little bit further and try to see whether they can deliver what has been seen in the calculations. So one could also ask why these other data are a little bit above what you see. Actually, we don't have a full explanation yet, but we believe that this is happening because in this other setup by the Columbia group, what they have is also a graphene layer, below the dielectric, and this graphene layer is screening a little bit the impurity scattering in their samples. So that should bring the mobility up a little bit. So that's something we're currently exploring to see whether one can even boost the mobility of the single material by adding some kind of semi-metallic layer like graphene to help. So now that was about the mobility of individual layers. The question is what happens when you try to build the device around it. So the one thing that is missing is the dielectric. So this is just an example of how we tackle the problem. So this is an example of molybdenum that is sandwiched between aluminum nitride, the dielectric on bottom and top. And this is just one of the many examples we tried. We had layers, we know 1, 2, 3, 4, 5, a few layers of aluminum nitride, top and bottom, to check what happens. So here I just want to share the key physics. So what is happening is that if you try to study this system, you discover that the phonon dispersions are modified. So the red lines here would be the phonon dispersions that you see for molybdenum sulfide in isolation. And then when you add the aluminum nitride, you acquire the blue lines, which are actually the phonons of aluminum nitride. So in the same way, the phonons of molybdenum sulfide cause a reduction of its mobility because there is phonon scattering. What might be happening is that the phonons sitting that vibrate in this plane or in this plane may also affect the electrons that travel in this layer. So this is something one can look at by decomposing the scattering rate by type of phonon. So this is which phonons as a function of energy in molybdenum sulfide impact the mobility. And this is the phonons of the aluminum nitride layer that impact the mobility. It turns out this phonon here is a longitudinal optical mode that has to do with the interlayer sliding of the aluminum nitride and the molybdenum sulfide. And this one here is a ZO mode, means basically it's a dipoles vibrating perpendicular to the molybdenum sulfide plane. So these two things cause electrostatic potentials that fluctuate in time and essentially scatter the electrons as they travel through the layer. So this causes a reduction of the mobility by about 30% in these systems. So now the question will be how can one engineer dielectric layers in order to minimize this kind of effect? That's something we are working on. But that's a much more complex problem because we don't need to study just one material. We need to study interfaces. So that's really a much more demanding computationally. And then the last bit of the device I wanted to discuss is the contacts. So what we have been doing basically is to develop software to study what happens if you inject a wave function here. That wave function has to go through this barrier, then travel and go and exit on the other side. So this is a completely different problem because this is what we call an open quantum system. So you have electrons entering on one end and exiting on the other end. So this cannot be done with standard DFT. You need some Green's functions techniques. And this is done using a standard approach, which is called non-equilibrium Green's functions. In practice, what we can do now is to essentially study the density of states of the system and the potential barrier that the electrons see as you change the gate to source voltage. Here, for example, in this case, the device is off. And as soon as you apply a larger potential, the device becomes on because the electrons here can tunnel through the other side. So it is a standard kind of thing that you can calculate. The difficulty is to try to calculate in a predictive way by reaching the same level of accuracy that we can for the mobility. So this is a much more complex question. And I would say that there is no software today available that can give you answers for this problem that are truly reliable to the level of a few percent. I think the inaccuracy and the uncertainty in this calculation is much, much higher. And it will take a few years before getting to fully predictive calculations. Now I just want to tell you a little bit, if I have 5 minutes to just explain what is the software infrastructure we developed to do this. So all of this requires a lot of effort in coding. So most of it is based on a piece of software that is called EPW. Actually, this started when I was a postdoc. And when I wrote the first version, it was barely 1,000 lines. And with multiple postdocs and then postdocs who became professors and then who have their groups and their own postdocs and students. So these are grown into something which is more than 100,000 lines now. And of this code, I know pretty much 1% at this point. But fortunately, I have very talented students and postdocs who can take care of it. And this is now a component of something called Quantum Espresso that maybe if you've done any DFT calculations, you will know. So that's a very big software package for material simulations that is open source and then many of us contribute to. So the EPW code now is such a big operation that basically is handled by a steering committee, which has 5 members, plus a few newcomers from Asia and from Germany. And there are essentially about 30 developers, which are postdocs and students in our groups. And it's an evolving story where everybody tries to contribute. And we try to structure the development in a way that is, you can proceed in a way that is sustainable, let's say, as opposed to create some code that then you put in a drawer and nobody can use in the future. Some of the things that I discussed require a lot of compute power. So a lot of effort that we do goes into the optimization of these codes. So the typical things that we need to show our sponsors when we try to ask for money to develop codes is that we can scale on supercomputers. So this test is what is called a strong scaling test. So what this plot means is that if I double the number of cores, computing core, I expect the time of the calculator to go down by a factor of 2. If that happens, I say I have a speed up of 100%, okay? If it's less than that, it means that something is not ideal in my calculation. So what we did here is to request from TAC that they kick out all of the users of the machine, which are hundreds of users, to let us use the machine for 24 hours. And we managed to scale the code to the entirety of the machine, which is 400,000 cores. And at this level, we have a speed up of about 90%. So that's just to show that the code has been completely refactored to leverage the best supercomputers available today. And if you notice here, there is MPI, OpenMP. These are technical words, but I'm not mentioning GPUs, graphic accelerators. So you will know, I'm sure you know that GPUs now are becoming the new paradigm in computing. So one has to do an effort to also be able to run on those machines. And in fact, if you look at the top 10 supercomputers in the world, the number 1, 2, and 3 are 3 US computers, which are El Capitan, Lawrence Livermore Lab, Frontier, Oak Ridge, and Aurora at Argonne. And all of these 3 are essentially GPU-based supercomputers. So to use those and to please our DOE sponsors, we must be able to use the code on these machines. And this requires, again, a heavy refactor in all the software code base. And these are just tests to show you that at this point, we're at a situation where the previous version of the code has been accelerated almost 10x, means that whatever we can do before, now we can do it 10 times faster by using GPUs. And this is also another test to show that it is not only just working on a single GPU node that needs to be accelerated, but also working on many GPU nodes. So if you can do acceleration only on one node, that's not good enough. So these are tests on the Aurora supercomputer. So this is the second most powerful computer in the world at Argonne. And here we managed to scale almost linearly to 6,000 GPUs. So that's basically a calculation, let's say, of molybdenum disulfide done in essentially 1 minute on 6,000 GPUs, okay? So that's basically the state of the art of what can be done today computationally. And I just want to also make a point that all of these calculations are becoming very complex. So the more software we have available, the more techniques and the more features we want to calculate. So a typical calculation now includes DFT, where you do some energy and structures. Then you need band structures. Then you need to do the phonons for transport. But then this has to be paired with some kind of transformation to make this the calculation of the phonon electron scattering efficient. And this requires something called Wannier functions. And then out of that, you need to calculate carrier transport properties like the Boltzmann equation. And since DFT band structure are not very good, you need to use GW perturbation theory, which are essentially many-body methods. And to do all of this, essentially each of these boxes is a bunch of files, input and output, where something can go wrong. In practice, you need to orchestrate at this level at least 4 pieces of software, which different languages, different input and output, different conventions. And the chance to go wrong, it's very high. So new students, for example, may take 1 or 2 years to just be able to perform confidently one of these calculations. So clearly this is becoming unmanageable, and because the complexity is skyrocketing. So what we've been doing in the group is to try to simplify all of this. And essentially the idea was to develop a Python-based interface that takes care of most of the complexity for you. And the philosophy is very simple. So the decision was we need to have some kind of wrapper that allows you to do a simple calculations in 2 lines and a complex calculation in maximum 10 lines. So this is the result of this object that we call EPWPy. Essentially, the idea was to design a calculation so that a material is an object, and properties of these materials are Python functions on this object. Okay, and this allows us to go towards automation, reproducibility, metadata that can be released for others to use, and so on. And the other thing that we've been doing, and this is a bit of a more like community operation, is to work in collaboration with NSF and with the Texas Advanced Computing Center to make all of these available on the cloud. So most of this software is something you need to install, you need to run, you need to find libraries and things like that. So that can be a barrier for new users. So the dream here is that anybody soon will be able to do these calculations without knowing much of the underlying infrastructure. So at this point, we have this platform, MATSI, that one can log into TAC and lands onto Jupyter notebooks that run directly on the supercomputers. And you can just use the Jupyter notebook interactively without knowing anything about the compilation, which codes are inside, and all these things. So the idea is to make this as easy as possible so that the community of users can become much bigger, and the barrier to entry may be decreased a little bit. So this basically brings me to the last slide, and I guess there was a question at the beginning, and the question was, can we design transistors one atom at a time? I think you can tell from what I just described is that we are not there yet, but this is going to happen, I think. So I don't want to give numbers, but I would say within 5-10 years, these things will become reality because the methods are increasing very fast. Software sharing and collaborations between software developers is becoming very efficient. So it is very possible that all of these things will really be developed very fast and in a very consistent and predictive way. So that's basically the last slide. I just want to say that the work that is done, I presented, was done by 4 amazing people. So Anne is the main guy on 2D materials and discovery and high-throughput searches. Abu is a student who's been working on the moly and aluminum nitride dielectric interfaces. Sabia is the lead developer of all these codes and basically coordinates the entire development activity. And then Tayoun is the one who realized the GPU porting of all the codes, for the supercomputers. And then we have a bunch of collaborators and sponsors. And I would say that this is probably the main sponsor for this research. So the Semiconductor Research Corporation, to something called the Supreme JAM 2.0 Consortium. Okay. So this is what I want to tell you. And thank you for your attention.
I think the floor is open for questions from the audience.
Really nice talk. Thank you. Slide 23, you showed the range of mobility for reported literature for MOS2. And as experimentalists, I want to report what, maybe what you can best compare to your calculation. So is that range like field effect mobility, effective mobility, Hall mobility?
That range is Hall mobilities.
All just Hall mobility?
Yeah, yeah.
Oh, okay. And then it's kind of a follow-up is on the WS2 work out of Columbia, they did this on ruthenium chloride, right? So should we be reporting Hall mobilities on van der Waals solids to best get to the theoretical limit?
Yeah, that's a great question. I don't know the answer. I think, let's say one challenge in those things was that, one challenge with these materials specifically is that the realizing p-type contacts is challenging because the work function is very high. So their claim is that with ruthenium trichloride, here they managed to achieve good ohmic contacts, but others are not been reproducing that yet. So that's really a question of, is that the reason why it works so well, or there is something else? For now, at least their claim is that this getting good p-type contacts was key, and getting low impurities. But I don't know more than that. So I can also say that some groups are skeptical. Because there are 2 groups who produce this data. I guess other groups are trying to reproduce them at this point.
I have a follow-up question. As a follow-up, if groups are skeptical, but they matches your prediction, what does that mean for you?
Well, for us, it means that we are hoping that other experimental groups will come up with similar data.
Yeah. So they should have good confidence in their results, right?
Say it again.
They should have confidence in their results because it matches the.
No. The experiments, the ones publishing this data are very confident about the results. It's just that the other groups are not able to come to get the same mobility. So I guess until a few other groups will be able to put the same numbers out, there will be still, the jury will be out there.
Are these defect concentrations?
These are just, this is basically the carrier densities.
Okay, thank you. Other questions?
On the steps on screening the 2D materials, Yeah, but yeah, there you go. You do electron mobilities or effective mass a couple times.
This one here.
Yeah.
So yeah, this is just a practical choice. So first, the mobilities are done without spin-orbit coupling. And because spin-orbit coupling is 64 times more expensive than for those that are not outrageously heavy, one it does them more carefully with spin-orbit coupling, basically.
Okay, got it. I missed that.
Yeah.
Yeah.
Yeah, I didn't mention it. It was a little bit technical. Yeah, sorry.
Feliciano, this is wonderful. Thank you. I'm wondering what advice you might have for undergraduates that are looking to get into theory and computation-focused research around materials, and maybe any stories about good training or coaching for working across theory and experimental collaborations, patterns that you've seen worked well.
Yeah, it's going to be a long answer. So well, let me say, maybe I don't want to advertise, but so I came from physics, and then when I was assistant professor, so lecturer in Oxford, so they asked me to teach a course on modeling, like using DFT for undergraduates, and then basically there was an experiment because people were recognizing these techniques could be useful. So we introduced a course on materials science. Basically, it was called materials modeling using density functional theory for maybe third year undergrad in materials science. And because of that, I ended up writing a book about it because I found that there was no book that for that level. So basically, there is a book that only assumes elementary quantum mechanics and then brings you into these calculations. Then because of that, in 2016, basically, I was roped into a program, which is one of the MIP, the Materials Innovation Platforms from NSF, the one at Cornell, where they promised NSF that they would teach DFT to experimentalists. So for 4 times in a row, every 2 years, I went to Cornell to do a week-long summer school to precisely teach these things to people with zero background. And I think the experience was positive because what happens is that it's just a matter of language barriers in the sense that if every book uses advanced theoretical physics to explain it, of course, the barrier is enormous, but most of these concepts don't require that. So just a matter of rewiring the teaching. And so we've seen that a lot of experimentalists that we train, I mean, they don't become computational people because in the end, it takes time. So if you're an experimentalist, you need 100% of your time. But they become fluent enough in these techniques, they can converse with their colleagues and at least establish collaborations and also challenge theorists when they want to sell or short sell some results and not really up to scratch. So the experience was very positive. And because of that, when I moved to Austin, actually, I advocated for creating courses on that. But this semester, so in fact, yesterday was one of the classes, I'm teaching density functional theory. And that's actually, we have people from material science, electrical engineering, chemical engineering, chemistry, physics, and and that's basically a lot of diverse people in terms of background, and they all seem to enjoy it. The point is to try to find a common language that does not have as prerequisite something that is very specific to a given degree. And that's doable, it's just a matter of spending some time in it. So I hope that basically this kind of interdisciplinary approaches to teaching will become a little bit more widespread, because otherwise it's too much siloed. Yeah, I'm very optimistic actually. So I think it's going to be more and more kind of blended knowledge.
Very nice talk. You had mentioned a defect density of like 10 to the 12 centimeter to the -2 as being kind of a threshold for where experiments were not matching the theory. Was there a particular type of defect that was dominant, or?
So this is ionized impurities. Basically, that would be sulfur vacancies, essentially.
Gotcha. Okay, thank you.
If there are no more questions, or specifically no more students' questions, because we have heard a lot of faculty asking questions, what are you students afraid of? Us judging? No, we are not judging. Half of us understood a quarter of what he presented anyway, so don't be shy. Okay, if there are no student questions, I think let's thank Feliciano again for the wonderful presentation. We're going to have another shared chemistry MSc seminar in 2 weeks, another computational one. And you may guess we invited the speaker. And see you guys in 2 weeks.